All right, here we go. Let's work on more proofs. Proofs involving congruent triangles. We're going to take a look at ways that we can prove triangles congruent, and we'll look at three shortcuts that we can use in proving triangles congruent so that we don't have to prove that every side and every angle of the triangle are congruent. We'll find a few shortcuts that help us simplify that a little bit easier. All right, so the first thing we'll explore is side triangle congruence. See if we can form a triangle, how many different triangles we can form if we have the sides all the same. So 6, 7, and 10 are the lengths. Let's see what kind of triangle I can form. See if I can get these sides to meet. I got 41 degrees, 105, and 34. Okay, let's see if I can find another triangle using these same side lengths. It's like the only way I can get them to meet, they're in the exact same spot. And you can try this one on your own. I provided the link on the website. There we go. There's another triangle. Notice same angle measures. So no matter what I choose, as long as I have sides that meet, I'll always have only one kind of triangle. There's only one possible place where those legs of the triangle will meet. And so that we will refer to as the side, side, side. Notice angles are the same as the one that I formed up here. So side, side, side congruence, or SSS, we'll call this one for short. So we can put that into our notes when we use the SSS congruence postulate. And we'll list that in our notes later on after we take a look at the other explorations. Well, let's work with the SSS for a little bit here. All right, so since we know that a triangle, there's only one way to form a triangle if we know all three sides. We can prove two triangles are congruent if we know all three sides in both triangles are the same. So if we take a look at this triangle, we know FJ is the same as HJ, and we know G is the midpoint of FH. And we want to prove that the two triangles FGJ and HGJ are congruent. So, well, we know that FJ is congruent to HJ. That's given to us. And since G is the midpoint of FH, we know that FG is congruent to HG. So now we've got two sides of the triangle congruent to each other. And we know JG is in both triangles. So by the reflexive property, we know JG is congruent to JG. So by SSS congruence, or the side, side, side congruence, we know that the two triangles are congruent. So pause the video, take a look at the two triangles below, and see if we can prove that the two listed triangles are congruent or not. Restart the video when you're ready. So triangle JKL and triangle MKL, we see that we have one set of sides congruent, two set of sides, and they share a third side. So we'd say, yes, those are congruent by the SSS congruence. Then triangle RST and triangle TVW, we have one set of congruent sides, another set. And then this side, RS and TV, we aren't sure what they are, so we cannot prove congruence unless we know that third side. So SSS is a shorter way to find congruence. That way we don't need to find all three angles as well. Because we looked at that exploration, found if all three sides are congruent, the angles have to be as well. So let's take a look on the coordinate plane. If we have a triangle DFG at -2, 4, F at 4, 4, and G at -2, 2. Oops. Move that one up a little bit. And we have triangle LMN at -3, -3, -3, 3, and -1, -3. So we want to determine if these are congruent. So the way to do that would be to take a look at the side lengths. So DF is 6 units. DG is 2 units. FG, since that's a right angle, would be equal, if we use the Pythagorean theorem, 36 plus 4 is c squared. C squared is 40, so square root of 40 is c, which we could simplify as 2 square roots of 10. Okay. Ln is 2 units. 1, 2, 3, 4, 5, 6 units up. And we would have the same variables. We could fill in the same variables for the Pythagorean theorem, find the value of c. And we see that we'd have the same equation over there. So c is going to be 2 square roots of 10. So we'd say yes, they are congruent by SSS, side, side, side. Now, let's take a look at SAS triangle congruence and see if that works. So what happens if we have two sides and the angle between those sides? So we refer to that as the included angle. All right, so how many triangles can we make if we have the side and the angle in between the two sides? So side AB is 12, AC is 6, and the angle in between them, the included angle, is 52 degrees. So how many triangles can I make? Notice here the angles are 52, 99, and 30. And no matter what I do, this side's not going to move. This is the only side that can move, which means there's only one spot that I can put this. There's only one triangle that can be formed if I know the side, the included angle, and the other side. So that's the next shortcut we'll use, the SAS congruence. All right, so we're going to work on a proof now that applies the SAS congruence. And in that proof, we have two triangles that we want to prove congruent, triangle ABC and triangle CDA. Can we prove those congruent if we know that BC is congruent to DA and BC is parallel to AD? Take some time to see if you can come up with that proof. Pause the video and I'll show you how I proved it when you're ready. All right, so first and foremost, I showed that BC was congruent to DA because that was given, and BC and AD are parallel. It's also given. And if I know the lines are parallel, I know BCA has to be congruent to DAC because these would be alternate interior angles. And alternate interior angles are congruent if the lines are parallel. So that gives me an angle and a side. Next, I can find the next side because AC is included in both sides of the triangle. Because the reflexive property, I know AC is congruent to AC. So I have a side, an included angle, and a side. Side, included angle, side. So by side angle side congruence, I know triangle ABC is congruent to triangle CDA. Okay. In the diagram, QS and RP pass through the center M of the circle. What can we conclude about MRS and triangle MPQ? Well, let's write down what we know. I know angle SMR is congruent to angle QMP because those are vertical angles. I know MS is congruent to MQ because those are radii. And I know MR is congruent as well to SM and QM. And it's also the same as PM because those are all radii of the circle. So I know triangle MRS is congruent to triangle MPQ by side angle side congruence. Okay, so our next exploration is HL. H stands for hypotenuse, L stands for leg. And you know that when we have a hypotenuse, we're dealing with a right triangle. So if I know the hypotenuse is 5, the leg is 4, and I know I've got a right angle here, how many triangles can I make? So if I drag this leg around, I see I get a triangle with 53 degrees and 37 degrees. The only other way I can form that is if I go below here. Notice I have 37 and 53 as well. So there's only one type of triangle I can form with the same length, hypotenuse, and leg when it's a right triangle. So HL would be another congruence shortcut. If I know the hypotenuse and leg in a 90-degree triangle, a right triangle, I know that there's only one type of triangle that can be formed. The next one we're going to take a look at is SSA. So if we take a look at SSA, we're looking at the side, and then the angle not between the two sides. So if I know that side AB is 14, side BC is 10, the angle is 40 degrees, how many triangles can I make? Okay, I can have a length of 15, 64, 75, and 40. I bring that side down some more, I get another triangle that has a side length of 6 and 1, 16, 40, and 24. So judging by that, we see that if I know the side, and the angle that's not between those two sides, I don't get a unique triangle. I have two possibilities. Even if I change the angle, change the side lengths, I see there's more than one possibility. I can form a triangle that looks like that. I could also make one, an obtuse triangle like that. So SSA is not a congruence shortcut. All right, so let's do another proof that involves the hypotenuse leg theorem, or HL for short. So let's mark down what we know. AC is congruent to EC. AB is perpendicular to BD. And ED is perpendicular to BD. We also know AC is a bisector of BD. If it's a bisector, that means it splits those sides in half, which means those are the same. We're trying to prove triangle ABC congruent to triangle EDC. So right now I see that I've marked up a hypotenuse and a leg, and I know it's a right triangle, so let's put that all in writing. So AC is congruent to EC, that's our hypotenuse, and that's given to us. We know AB is perpendicular to BD, ED is perpendicular to BD, that's also given to us. Because they're perpendicular, we know those are right angles, because that's what perpendicular lines mean. So triangle ABC and triangle EDC are right triangles. It's just the definition of a right triangle. You've learned that a right triangle has a right angle. And we also learned, or we're told, that AC is a bisector of BD. Another piece of given information. And because I knew that that was a bisector, I knew BC was congruent to DC, because that's what a segment bisector does. It splits a side in half. So that gives us the L, the leg. So I've got H and L. So I know the triangles are congruent by HL congruence. So you'll find that we're kind of getting into an alphabet soup. And we're kind of using all these abbreviations, HL, SSS, SAS, to help us find shortcuts to prove triangles congruent. So let's go ahead and list all those congruence postulates so that we have them in writing now. So the SSS is already filled in for you. If all sides are congruent to all three sides in another triangle, triangles are congruent. Same thing, SAS. So if we have two sides and the included angle of two triangles, and we know those are congruent, the two triangles are congruent. So in this example, RS congruent to UV, included angle R congruent to angle U, and side RT is congruent to UW. Side included angle side. So triangle RST congruent to triangle UVW. And we want to be certain that we get that congruent statement correct in the right order. So RST, UVW, matching up the same sides and angles. And then finally we learned about the hypotenuse leg congruence theorem, or the HL. So if the hypotenuse, BC, is congruent to EF, and the leg, AB congruent to ED. So if we have H and L on a right triangle, triangles are congruent. Remember, it's very important that it's a right triangle because we found that if it's just side, side, and any angle, that is not a congruence statement. So that's one to remember. All right, so this is a good summary of what we learned. The SSS congruence, the SAS congruence, the HL congruence, those all work. SSA does not work. Have a wonderful day. We'll see you later.